All right, today, section 13.1, functions of several variables. So you guys are very comfortable with working in two dimensions, right? You have one input variable, we usually call it x, and you have one output variable, and we usually call it y, or in function notation, we call it f of x. So what we're going to do is we're sort of broaden our perspective of what functions look like to have more than one input variable, okay? So the first one that we're going to look at is a function of two variables. So what is a function of two variables? Well, this is a rule that assigns one output. We're always going to have one output value. But we're going to call it, instead of calling it f of x, it's going to be called f of xy. So one output value, and it's a real number. In fact, I'll just put that in parentheses, just to remind you. We are working in the real number system still. To each ordered pair of real numbers x, y. So in this case, we have two inputs, x and y, and we're going to have one output. And not only are we going to do that, because we did that in Calc 3, but it's going to actually be a function now, right? So it's exactly one output for each input. Now, we encountered some images in Calc 3 that weren't functions, things that look like spheres or ellipsoids, right? You guys remember those? So there wasn't just one output for each input value. So this doesn't always happen, but when it does, it's called a function. All right. Let me write one more thing before I write that. Okay, so this value xy is in the domain of the function. So we still have to talk about domain values and what works and what doesn't, which is actually where we're going to start. The domain of the function. And then we sometimes will see written our function, we'll call it f like we did before, takes the domain, which is a subset of R2, so two-dimensional space, and it takes it into one-dimensional space, one output dimension R. Okay. You guys seen that notation before, used in other math classes? Have you? What math classes have you seen it used in? Do you remember? What did you know, Caleb? What did you say? In Dr. Nichols' classes, you saw it that way? You'll often see it done and written that way in analysis or algebra, if you've taken any of those as well. And just remember that this means it's a subset, so the domain is a subset of the R2 space, or the plane, and we're taking it into one space, kind of like the third dimension, the z space, which is just the value r, or just the space r. All right, so the first thing we're going to do is we're going to do an example with some domain. So here's our example. We're going to describe. What does the word describe mean?
Describe.
When you see the word describe, what kind of an answer do you think your answer is going to look like? What
Words.
kind of words? There you go. You're going to have some words, right? Describe the domain of the function. So you mentioned Dr. Nichols, and you guys know that I don't expect you to have to write full sentences for everything, but when it does say describe, I do expect some words to be written, okay? So the first one that we're going to look at is the function f of xy, and this is going to be 1 over x plus y. So domain is going to have to do with the values x and y now, not just x. Okay, so, algebra, trig, even, Calc 1 and stuff, domain is always about x, range is always about y. It's not that way anymore. Your domain is about the variables x and y because those are both input variables. So tell me something going on in this one that's going to be important for us to make note of.
X cannot equal y.
Very close.
Cannot equal the opposite of y.
Yeah, cannot equal the opposite of y. Right, Nathan?
Yeah. Right.
Yeah. So what would happen if they did?
0.
Yeah, we get a 0 in the denominator. And that is the only problem for this, right? Everything else is going to be perfectly fine. So you're going to see things with square roots, right? And you have to remember that underneath the square root, you can only have positive values, that kind of thing. You're going to see things with denominators, different stuff like that. So what are we going to write down? We've got this sort of note to ourselves that we know that x cannot equal negative y. So let's describe it. What are we going to say?
X and y at the beginning are very similar.
Thank you very much for saying that, James. Yes, so the domain is actually going to not say x cannot equal y. It's going to say x and y can be anything except something, right? So the domain is all x, y. Where x and y are real numbers, right? And if you want to use notation for that instead of writing the words out, you could say something like this: x and y are elements of R. That's the notation for there are element. Well, the E is the element notation, and R, of course, is real numbers. So x and y are real numbers. But we do have to make the condition that x cannot be negative y. Or you could say y cannot be negative x, which would be fine, of course, too. Does that make sense? And if we've just talked about domain, what do you think we're going to talk about next? Range. That's correct. So our next example is going to be the same thing, but dealing with range. So we're going to describe the range for the function. We're going to use the function f of xy equals the square root of 4 minus x squared minus y squared. And before we start talking about range, I just want to make just a pause here for a moment and talk about, if we were dealing with domain here, what would we have to sort of think in our minds, be considering? Yeah, no negative numbers underneath the radical, right? And we might even make a note to ourselves that there are certain things that x and y themselves are not going to be able to output, because the x and the y are squared, and we have to make those sort of, notice those sort of details as we're working through. However, we're working on range on this particular problem, and we have a square root. So what is the range going to be?
Have to be positive numbers.
Positive numbers. How come?
Because you can't get a negative from this one.
Right, so the range is going to be all of the output values, and the output values have to do with this particular, symbol. And whenever we have a square root symbol, we understand that that means the principal square root, which is the positive values, or 0, right? I mean, we could have 0 as well. So we're going to describe this. So we know something about the fact that we're looking at numbers that are greater than or equal to 0. This is sort of what we want to keep in mind. And we're going to describe this. So somebody sort of formulate some words for me that make a description for this.
Range is all x and y greater than or equal to 0.
Now careful, is it all x and y?
Apparently not really.
X and y are the input values. Range is the
Oh.
output. F of xy. So this is all f of xy. And if you want to, you could call that z. I mean, that would be okay. We can do that kind of like we change the f of x into z or into y when we're dealing in 2 dimensions. So the range is all f of xy values. That what? They have to be positive. Now, is there any, they definitely have to be positive. Is there any cap on how positive they can be? Is there a biggest value possible kind of question, or is there not? So that's a little trickier. If you think about it, sometimes there is in terms of 2 dimensions. So let me just take a little aside here for a moment and think about what happens when you have just like a basic circle in 2 dimensions. So in a function notation, it would be a semicircle, right? And the notation would look something like this. Instead of saying x squared plus y squared equals, say, 1, if we only get half of it, we get something like this where we say y equals the square root of 1 minus x squared. And that kind of looks similar to the function that we're dealing with, right? Yeah, in fact, the function we're dealing with is, in fact, what shape if we actually had the whole shape? It would be a sphere, wouldn't it? It would. So on the one that we're dealing with, we do have sort of an upper end of what it can be as well. What would it be? What's the biggest value I can get for my range value here? 2. 2 is the absolute biggest I can get. And that would happen when x is equal to 0 and y is equal to 0, right? And so if you're thinking in terms of 3 dimensions, this is sort of the top half of a ball or a sphere, and you're looking at that peak part on the sphere. So that are positive and less than or equal to 2. So we could write that notationally as something like this. 0 is less than or equal to f of xy is less than or equal to 2, if we want to write that all combined instead of in a sentence more format. So the range is all f of xy values that are bigger than 0 and smaller than 2, or equal to them. That's okay as well. That's really happening because of those squaring features, right? Because the x squared and the y squared, that's why we're getting that cap. I can't take something really bigger than, I can't get anything bigger than that because the x squared and the y squared have this only this ability to be positive once I square them. So that's what's happening. Any questions on that? Okay. Now, there's nothing special in particular about well, 3D is what we just did. There's nothing special about a function with 2 input variables. So we can talk about a function of 3 variables. That means 3 inputs is a rule that assigns 1 output, and then we call it f of x, y, z, to each, and instead of it being ordered pair, it would be an ordered triple x, y, z in the domain. Now, I wouldn't say this is a problem, but the reality is that we don't have the ability to draw this picture. Agreed? We can only draw in 3 space, and I can't draw in 3 space very well. So we don't have an ability to draw this. But if you imagine something like this, imagine like a mountain range, okay? So no matter where you are on the mountain range, you have a 3-dimensional coordinate. You are, longitude, latitude, and what would the third one be? Elevation or altitude, right? How high you are from above sea level, or however you measure it like that. So a 4th dimension to that could be something like the temperature, right? There's only one temperature at a given point in time at that particular 3-dimensional or ordered triple. So you could think of something kind of like that where it would work like this. In fact, I mentioned that because one of the problems you're going to look at is going to be something to do with, I think, a mountain range, and so it's going to have, not with temperature, but it's going to have that sort of a feel to it as well. So that would be a 4th dimensional idea. And again, there's really nothing even special about the fact that this was a function of 3 variables. We could do it with 4 variables as inputs or 5 variables as inputs, right? I mean, there's nothing really special about the number of them. Most of the ones we're going to work with, however, are going to have 2 inputs. Okay, so we're not going to work too much beyond that 2 input variable. All right, another idea in this, and this is where our mountain range is going to come into play in a little bit here, is the idea of something called a level curve. All right, so a level curve of the function f of xy is the, and I'm going to put it in parentheses here, two-dimensional, I'll even write 2D, curve defined by f of xy equals c for some constant c. This corresponds to what's called the trace of the surface z equals f of xy in the plane z equals c. Okay, so picture a real simple object right now. Just picture a sphere, okay? So it's definitely this three-dimensional object. It's not a function, so it doesn't quite fit in this definition, but it gives you the right picture in your mind. So picture a sphere, and picture taking a slice right through it, okay? So you've got your, tsunami, no, that's not the right word. What do they call those swords? What is it? Samurai, that's the word I want. You got a samurai sword and you slash right through the thing, okay? The slash mark that you make straight through that, presuming that it was level, of course, would be the level curve, the outline that you get when you do that. So you can again think of in terms of something like a topological map. So a lot of times you'll see maps that are drawn, but maps are usually drawn in 2 dimensions, right? So how do you draw a 2-dimensional map and also still be able to see like the elevation you're at? Well, you do it because they draw curves in, and the curve lines they draw in show the elevation. Those curve lines are called traces or level curves, okay? And they tell you, like, everywhere along this sort of curve that they've drawn is going to be an elevation of 1,000 feet or an elevation of 6,000 feet or whatever like that. So that's they use this in topological maps, this kind of an idea. Okay? And it doesn't always have to be like in my sphere example with my samurai sword. We actually slice it and it turns into a circle, right? That's the trace that we actually slice through. It wouldn't be that in a real life mountain situation, right? You're going to end up with funny sort of shapes, things that don't actually look very symmetric and stuff like that. But you do end up with a shape like that. Now, if you take one of those, it's called a level curve. That's just letting one of them. So basically what you're doing, and go back over here for a second, is you're taking this equation that was in 3 variables, and you're saying, let's let z equal something specific, right? Z equals 7. And once you do that, you turn it into a 2-dimensional equation, right? Because there's no z in it anymore. There's only an x and a y, and you know how to graph in 2 dimensions. So then you're able to graph what you're looking at for that one specific value for C, in this case 7. All right, so what we're going to do now is we're going to say, but what if we wanted to know what the whole image looked like, at least within sort of an idea of how this is working? Well, that's actually called a contour plot. So a contour plot of your function with 2 inputs, x, y, is a graph of many level curves. F of xy equals C for representative values of C. All right, so the practical point of what was here is that we are limiting how many values of C we're using because practically speaking, there are infinitely many values we could use, right? We're not going to use all of them, obviously, so we're going to choose a few values of C. The word representative means they need to be values that make sense, okay? So you're doing your altitude, of course, in a mountain range, you're not going to be measuring at 1 foot and 2 foot and 3 foot and 4 foot, right? You might be measuring in thousands of feet based on the altitude of the mountain range. If you're working in other functions where you do have smaller output kind of values, valid, then you might be using smaller values of C to do this. All right, so we're going to try one of these and see how it goes. So we're going to sketch the indicated traces and I'm going to put this in quotes because I want to come back to this idea in a minute, and graph, quote unquote, Z equals f of xy. So we'll come back to why I put that in quotes in a minute. How I keep drawing lines through things, but okay. So our first problem that we're going to look at about contour curves is f of xy equals x squared minus y squared. And then we're going to look at what happens when x is equal to 0, y is equal to 0, when z is equal to 1, and when z is equal to -1. Now, not all those things are happening at the same time, obviously. Those are 4 separate graphs that we're looking at. Something else I want you to be aware of is that this does not say graph the indicated traces. It says sketch. When they use the word sketch, what do they usually mean? Do you know? Yeah, you're doing an approximation. The issue is the shape, not exact values. So you don't necessarily have to draw in, as far as I'm concerned anyway, that x is equal to 1, this is y is equal to 1, and x is equal to 1, 0, and then this y is equal to 7, and you don't have to put details of that nature on there. You're looking for the overall image that you get when you hold something constant and change something else. All right, so let's do the first one, which is that x equals 0. So what happens when I have x equal to 0 with this particular function? And just for simplicity, I'm going to call this z for now, okay? So what's going to happen when x is equal to 0? We get z equals -y squared. Now, that's 2 dimensions because there's only 2 variables, right? So I can actually draw my picture in 2 dimensions. And just because I'm going to call the z-axis the vertical and then the y-axis is the horizontal, which I know that feels a little awkward still, but that's okay. What does the shape -y squared look like? I mean, what does this look like? It's a parabola. Tell me more. Upside down, right? And it actually would hit the origin and go upside down, right? So the overall image we're getting looks something like this. Agreed? And that's what we're doing here, okay? And you might even make a note to yourself here, because we're going to have this detail that we're going to use in a moment, that we're talking about a parabola shape here. Okay, and I'll show you how I'm going to use that in a minute. All right, the second one told us that it wanted to do it at y equals 0, right? So when y equals 0, what equation do I have that I'm working with? Z equals x squared. So what is this shape going to look like? Again, it's 2-dimensional. It's going to look like a parabola, but opening up, right? So we have this shape. So again, we have a parabola, and it might be good for us to now go back, because I didn't write it before, and kind of mention that this is opening down, parabola down, this is a parabola up, because they are obviously different.
Should that be an x instead of y-axis?
Yes, thank you very much. Good. All right, couple more. The next two say z equal 1 and z equal -1. And because we are holding the z as the value we put the value in for, we could draw these both on the same graph, or you can draw them on separate graphs. The solutions manual actually puts them on the same graph. I'm going to put them on separate graphs just to remind us of what that would look like separately, because I don't want you to think it actually makes up one graph. It's two separate graphs. So the first one here says z equals 1. So if z equals 1, what are we going to get? X squared plus y squared equals 1, right? Do you know what that shape is? It's a hyperbola, right. It's a hyperbola. So now you guys have to help me remember. I'm pretty sure I wrote it down right, but it's a parabola, excuse me, a hyperbola. Is it opening up and down or left and right? Is it?
I think the X is first, so left and right.
Well, one's one and one's the other. Well, the other one we're going to have is going to be flipped. This other one over here is going to be, oops, sorry. This other one for z equal -1 is going to flip them. I'm going to end up getting y squared minus x squared equals 1, right? So we're going to have one opening up and down, the other one opening left and right. So grab your calc book if you have it with you, and let's figure out which one's which, okay? Because we have two of you thinking two exactly opposite things, and I'm not going to guarantee that I drew it right when I wrote it down, so you guys are going to double check for me. Which one's which? Yeah, or you could check with a calculator since we are working in 2 dimensions and solve for one piece. That would be fine too. In terms of drawing yourself a I don't know, a reference, it's going to look, oops. You're going to have asymptotes going through here that we're going to be trapped between.
X squared minus y squared equals 1.
All right, so this one's opening like this, Nathan? Excellent. Well, somebody had to be wrong, right? And then this other one's going to open like this. Now, can you see why I might not want to put these on the same graph? It would kind of look like I've got this, I don't know, like boomerang kind of shape going on or something when I actually put them on the same graph, because they don't actually have any pieces that overlap or anything, and so it'd be hard to designate which was what. So let's write down that these are hyperbolas, like you guys mentioned. Okay, these are hyperbolas. Now, we've actually sketched the indicated traces, but we haven't, quote-unquote, graphed f of x, y. I didn't even finish writing that up here. Any ideas why I might not have graphed the f of x, y, or maybe why I've put that in quotes? What does it mean that it wants me to do, really? I mean, if I do exactly what this says, what am I doing? What kind of a graph am I going to get? A 3D shape. And I will tell you, I spent quite a bit of time trying to figure out how to draw this particular 3D shape, which I know exactly what it looks like. I can tell you exactly what it looks like. It looks like a horse saddle. This looks like a saddle, and I'm going to show you that on the computer here in just a second. I can't draw it. I just can't do it. And I don't think there is anything wrong with me for not being able to do it either, just so you know. I can't draw. And so when I put that in graph in quotes, here's what I would like for you to do when you get to this. If you can draw and you want to draw me beautiful three-dimensional shapes, more power to you. I would love to see them. But I'm also okay with you describing the image that you're seeing if you look at it and you do it on a three-dimensional grapher. Does that make sense? So if you put it in, we'll do it here in just a second together, and you get the image in your mind and you can describe it in words, I'm okay with you describing that instead of actually physically graphing it. Everybody good with that? Because I can't graph it. I'm not going to expect that you will either. All right, so let me go ahead and write down the description with you, and then I'll show you the picture of it, and you can agree that it does, in fact, look like this. So one of the things that we're going to write down is we're going to write down what this actually, I put parabola down, parabola up, hyperbola, hyperbola, and I want to actually write down these details. So this graph, so this is my graph. This is a parabola around the YZ plane, we'll say it that way, opening down. A parabola around the XZ plane opening up and a hyperbola in the XY plane. And then overall, we call this a saddle. So jot those down, and then we're going to take a look at the three-dimensional shape so you can see it. Yes?
It says, is a parabola spread around the YZ?
Yeah, the first one is YZ right here. This is YZ. Oh, it's because I moved something. This is plane. YZ plane opening down, a parabola around the XZ plane opening up, and then a hyperbola around or in the XY plane. We do get a saddle shape. Okay, you guys ready to see the picture? See what it looks like in 3 dimensions? All right. All right, so I sort of put 2 definitions together, and I kind of made you believe that they were exactly the same thing. One of them was when I said level curve, and then I said right after that contour plot. All a contour plot is a bunch of level curves all on the same graph. So what we're going to do next is we're actually going to sketch a contour plot. Okay, and we're going to sketch a contour plot for a slightly different equation. We're going to do f of xy equals x squared plus 4y squared. Do you guys remember what this looks like, or at least might look like? I mean, what are you seeing some images of here? Yeah, there's some ellipse stuff going on, right? And in fact, if I let f of xy hold at a number, be a specific number, I should get ellipses, right? Yeah, I will. And so we kind of want to think through what kind of nice shapes we would want. Now, are there some things that y, or f of xy, excuse me, the output can't be? Think range here. What can't happen? Can't be negatives. Could it be 0?
Yeah.
Sure. What would have to happen in order for f of xy to be 0? Right. This would happen when x, y as an ordered pair is equal to 0, 0. Or you could say x equals 0 and y equals 0. Okay, so that's actually one trace. And just for the sake of continuing on, we'll call this z equals 0. Just so that I've got a shortcut way to write it. Okay, so z equals 0 when x and y both equal to 0. We're going to try another one that's a little bit convenient to use. So let's just pick another value for z. What might be helpful to let z be? 1. And that's nice because if we are in fact talking about an ellipse, the sort of ellipse form is typically set equal to the number 1. So if I have x squared plus 4y squared equals 1, it's not quite in ellipse form, but it's awfully close. Do you remember how ellipse form looks, like the standard form?
Divided by.
Yeah, it would be divided by, and right now I've got it multiplied by 4. Do you know how I fixed that, so to speak? But if we divide everything by 4, then it will divide the number 1 on the right by 4, and I don't want that to be divided by 4.
So let's z equal 4.
What's that?
Let's z equal 4.
No. Well, we will in a minute. I'm going to do a z equal 4 contour in a minute. Yeah, because that'll be really helpful. There's a trick. You usually see it done in oftentimes in a trig class. But what we could do instead, we are going to, of course, write that x squared's over 1. But instead of multiplying by 4, I'm going to divide by 1/4. That'd work, right? Yeah. And as a matter of fact, we'll take one more step just to remind you that when we're working with ellipses, it's actually more helpful to have the bottom written as something squared. And that actually works very nicely for 1/4 because it can be 1/2 squared, right? So this is going to be an ellipse. What can you tell me about the ellipse?
It's going to be along the x-axis. That's the major axis.
Okay. I'm going to skip over to this slide so we can draw it. Actually, let me try this. Okay, it's not cooperating. I'll try it later. That's fine. All right, so you said the x-axis is my major axis. And actually, well, I'll stop for a second. I'm about to tell you something else. So we'd go out 1 on the left and the right. What else did we do? We would go up 1/2, right? So the ellipse that we're getting looks something like this. What you do on a contour curve when you're drawing this is you have to write next to it what the contour is. So this would be z equal to what? What did we let z be? Was 1. Now we actually did z equal to 0 as well. What happened? What image do we get when z is 0? What is it? You can't hardly see it, but it's just the origin, right? When z was 0, x was 0, y is 0, that's a point. It sort of collapses down to a single point. So right here, and I'm running out of space because I should have drawn my picture a little bit bigger, but that was z equals 0 at the origin. That was my first contour. Now, I'm going to do exactly what Brandon suggested, and I'm going to skip. There's nothing wrong with doing z equal 2 or z equal 3, except that z equal 4 is so much easier to do. So I'm going to skip to z equal 4. As long as I'm labeling my contours, I can choose what values work well anyway. So if I let z equal 4, then I have x squared plus y squared plus 4y squared equals to 4. And then what can I do? Yeah, now I can actually divide everything by 4 so that I get equals to 1 on the right. So now I have x squared over 2 squared plus y squared over 1 squared equals 1. So the shape's still an ellipse, right? In fact, it's always going to be an ellipse. But what's going to happen in my ellipse shape now?
Go back to 2 and 1.
Look at that. I've told my students before they can do that, but I've never actually done it in class, so that's fun. All right. Yeah, so we're going to go out to 2 on the x-axis, and we're going to go up to 1 on the y-axis, which was already there. So here's the 2 values, and then up to 1 and -1. And then I'm going to draw a bigger ellipse out here. And then we'll label this as Z. Equal 4. Now we didn't do Z equal to 2 and Z equal to 3, but where are they? They're in between, right? So if we were to draw Z equal to 2 and Z equal to 3, and it would look like concentric ellipses, correct? They would just be broadening as we get further out. So this looks like an elliptical shaped bowl, doesn't it? And you can almost have the feeling that you're looking at it that way. What can you tell me about this point here if you were only given this map, this picture? What could you tell me about the point at the origin? What would it be on this particular graph in 3 dimensions? It would be the bottom of the bowl or the top, depending on the graph. This is Z equal to 0, so it would be the bottom of the bowl, right? If this were the highest value for Z, like if it worked its way outward and it went decreasing values of Z, then it would be the top of a bowl. So this is the bottom of a bowl. We have another name for that in math instead of bottom of a bowl. Any thoughts? We sometimes have called a vertex, at least in 2 dimensions. More general than that, though. That's awfully specific. Awfully specific to something called a parabola, right? Or to actually an ellipse, we actually mean vertices are the endpoints, not this, right? Minimum or maximum. Very good, Jordan. This would be a minimum, right? In general, we would call it a relative extreme point. This would be a relative minimum value. And in this particular graph, it would be an absolute minimum value as well. And if you look ahead in terms of titles of sections, we're going to be getting to that idea very soon, the idea of relative extrema. All right, so I'm going to give you a homework assignment, and you guys can break apart into, since we have 8, I guess you can break apart into pairs would work well. All right, so this is on page 818. Number 2 and 4. On these 2 right here, you don't need to sketch. Okay, it asks about sketching. You don't need to sketch. These are questions about domain. And then we have 8, 10. And then on 17 and 18, it tells you that thing like where I said graph, and I put the graph in these quotes like this. So where it says graph right there, if you prefer, you may describe instead of graph. And then we have 27, 28. Both of those are matching, okay, just to kind of give you a heads up. And then 30 and 31 are sketching level curves. And then 53 and 54 actually look at like a topological kind of map. Okay, so they look at an application of something, I think it's in a mountain range that you're looking at. All right, go ahead and find a partner.